Welcome to the 25th lecture video for Physics 4C. Having finished the introduction to wave mechanics, now is the time to get into the fun details. This week, we start by looking at the features of the solutions to the three-dimensional Schrödinger equation for the hydrogen atom, and the quantum numbers, the principal quantum number, the orbital angular momentum quantum number, the magnetic quantum number, and the spin projection quantum number, the quantum numbers that are used to characterize the atomic state. I will draw some level diagrams to illustrate the complexity of atomic energy levels arising from these, and talk about how the Pauli exclusion principle, something maybe mentioned in chemistry, comes out of the symmetrization requirement for indistinguishable multiparticle systems. Oh, and I will also describe the process for obtaining solutions to a three-dimensional particle in a box set up in some detail. This is a long lecture, and I hope you find the details here interesting, because there's more to come.
Welcome back. So far in this class, we've been dealing with some made-up examples. Like infinite square well, it's one of those made-up examples. And that's where we are kind of limited to, because we live in three-dimensional world. If you're going to deal with the real things, it's going to be three-dimensional. And as you will see in some glimpse of the math that's required for the working out the hydrogen atom, the calculus for that becomes very difficult very quickly. So this is sort of the end of where we are actually working out the differential equations. And now I'm just going to point to the results that's been derived. And it's going to actually overlap quite a bit with something you might have seen in your chemistry class. So reminder of a hydrogen atom. So you know what hydrogen atom is. It's a proton with electron orbiting around it. That's a classical statement to make. You don't say that in quantum mechanics. So for a fully quantum mechanical treatment, your starting place has to be the Schrödinger equation. This really has to be your starting place. And so far, we have been dealing with the Schrödinger equation in 1D, one-dimensional. You can kind of notice that from the variable x. I haven't so far mentioned the y or z. And with the hydrogen atom, it's a three-dimensional object. So proton at a point, let's say it's at rest, it doesn't move. But electron is going to be moving around all over the place. And you need to have a three-dimensional wave function that describes the electron. So solving for the hydrogen atom means finding a wave function for the electron in 3 dimensions. And when you just look at this, you might look at it and think, oh, that looks fairly reasonable. It doesn't look at all complicated. And that's because I have taken advantage of notations that make things look simpler. The biggest thing I have done is I have made use of these vector notations. So whenever you see vector, that's your cue to be aware of, like, check yourself. Make sure, do I understand what the notation means? Because what each of these means is that that function that's written there, seemingly as a function of one parameter, is actually a function of 3 parameters, x, y, z. So before you do anything, or this is a Cartesian coordinate, or if you use a polar coordinate, then it will be r, theta, phi. By the way, be careful with the polar coordinates. The convention for mathematicians and convention for physicists is exactly the reverse, how we use theta and phi. For us, theta is the azimuthal angle from z, and phi is the whatever the xy thing is. Mathematicians do it the other way. We are doing it the correct way. And same thing for v. So v, in general, is going to be a function of x, y, z. Now, it turns out an arbitrary function like that is very difficult to deal with. And that's really the reason you would ever be using spherical coordinates, is because you are dealing with what's called central force, central potential. Well, whatever is where the potential is a function of r only, no angular dependence. And this actually describes a lot of things. Gravity is like that, electricity is like that. So it actually describes a lot of things. But so that's what all this complexity is what I am hiding behind this seemingly simplified notation is equal to E psi x, y, z. And really the biggest offender here, well, not offender, biggest simplification I have gained is this Laplacian. I was talking about it a little bit before class. This is a wonderful notation that actually accomplishes two things. When I write my equation this way, one, I'm writing it in a way that's a coordinate independent. So this is the correct equation, whether I choose Cartesian or polar spherical coordinate. So this is like a good general equation to remember. And that's one. And the second thing is it reduces all this number of letters I need to write down. So let me just expand this out, because this is hiding just so much that it's easy to forget how complicated of a mathematical object Laplacian is. So do I want to? Yeah, I don't think I have. Do I have? I think I have space to write it out here. So let me do a version here. So this is what that Laplacian means when you write it all out. When you write it all out, well, let me do it first step. What Laplacian represents, it actually represents an inner product. It represents a dot product of gradient to itself. Do you guys remember what gradient was in that 3C? Yes, kind of. I'll just write it out. I won't ask you. So I remember gradients well in the Cartesian coordinates. So I'll do that in Cartesian coordinate first. So gradient is the x hat partial derivative with respect to x plus y hat partial derivative with respect to y plus z hat partial derivative with respect to z. That dotted to itself. X hat partial y hat partial plus z hat partial. When you take the dot product, it actually becomes a little bit simpler, because only x hat dot x hat is not 0, it's 1. So I get double x derivative, double partial derivative with respect to x, plus double partial derivative with respect to y, plus double partial derivative with respect to z. So this is what Laplacian is. So this is actually simple enough for me to write down here in the expanded version of this expression. All right, so that, just write it out here. So these are all operators, by the way. So I have factored it out to the left so that I don't have to write down as much. But for you to do anything useful, you kind of have to remember to apply this to the function that it's acting on. And I still have these coefficients, so let me finish writing them now. Minus h bar squared over 2m. So this is one version of Schrodinger equation in 3D. And you know, this is actually doable. If we had like an extra day, you could actually do this with a 3-dimensional infinite square well. It's actually doable. Now the problem is you are not dealing with the infinite square well. You are dealing with electrostatic potential, meaning we are dealing with this potential here, right? So, all right, fine. So let me rewrite this potential in terms of that. Minus k e squared over r. But that's wrong, because I'm writing this equation in terms of parameters x, y, z, Cartesian coordinate. I cannot just suddenly put in spherical coordinate variable. So I have to rewrite r in terms of my Cartesian variables, meaning this is square root of x squared plus y squared plus g squared. So staring at this, I don't get great confidence that I'm going to be able to do this. So I'm not going to. I just wanted to show you that it is a very complicated equation that takes a lot of mathematical tools to be able to do it. And really the way to do it is by using the polar representation, where the potential is written more simply minus k e squared over r. But when you do that, there's a trade-off. Your Laplacian becomes super complicated in the spherical coordinates. I don't even remember that. I always look it up. I never write it down. So this is all to explain that we are not going to do this exactly. So I'm going to just quote the result that comes out of it. So here's one result that comes out of it. I said that just now, I said that if you had to do this for infinite square well, cubic square well, then you could do this, right? That's what I said. And when you do it that way, the way you do it is by what's called the separable solutions. It turns out this three-dimensional wave function, it can be under special circumstances. You can find kind of basis or kind of almost like unit vector-like solutions. You can find these forms of solutions. That if you are looking for general three-dimensional solution, if you are dealing with like a Cartesian system, like an infinite cubic well would be, then you could actually write it, solve it into this form. Big function x as a function of x. This is not a good name. I'll go with it. Capital Y in terms of y, capital G in terms of g. This is what's called separable solution. I think you might have heard this term before. Separable solution, yes? Right? Yeah. And that's the technique that you use. And in fact, once again, if we had an extra day, you could do this with infinite cubic well. It's actually doable. What's difficult and what we are not spending a lot of time on is how to do that for the spherical coordinate system for this potential. And what I'm going to do, I'm just going to cite the result. That when you write all this out, there's a form of differential equation. And for the hydrogen atom, this function of radius, azimuthal angle, and whatever the other angle phi is, you can separate this into two solutions. You can separate into the radial function, which is going to be a function of radius alone. And you can separate it into angular function. That's a function of theta and phi. And this actually has a special name to it. Now, let me just give you the name so that you can look it up or whatever. This is called spherical harmonics. And it actually occurs in essentially any time you're dealing with central potential that depends only on R, then you can separate out your solution and the angular portion becomes a spherical harmonics. So that's the description you will see in your textbook, like going through this, et cetera, et cetera. You know, read through this description of the, this is our convention, and as long as you're in a physics class, you follow physics convention. And so where they're separating this as theta and phi, I'm just combining that as a spherical harmonic. But so what it is I wanted to stop here. So there are parameters that characterize each of these solutions. And this is, we call them quantum numbers. And this is what you might have seen in your chemistry class. And that's what I want you to spend a little bit more time on. So when you look at this radial function, there are going to be two parameters that characterize it, n and L. And when you look at the spherical harmonics, it'll be characterized by all three quantum numbers that we are going to introduce, n, L, and m. And I guess you've actually seen one of these three quantum numbers before. Do any of them look familiar?
The N, right?
N, yeah. So this N is actually the same N you saw in the Bohr model. So we call N principal quantum number. And in the Bohr model, I guess the key thing that came out of the Bohr model was that your energy was equal to minus E naught, or for hydrogen, 13.6 eV divided by N squared, right? That's what you had in the Bohr model. And this is the one correct result out of the Bohr model. This is still correct in this quantum mechanical, fully quantum mechanical treatment. So this N is the principal quantum number, and I guess the best way to associate some kind of intuitive sense to that is to think of it as it tells you how far the electron is away from the proton on average. Now, you cannot nail down a specific distance. That's where chemists use the visualization of an electron cloud. But on a general rule, this N tells you how far. Well, let me go over the other two quantum numbers. L might look similar to the other quantum number you have seen before. Where else have you seen the letter L before? Sorry, it's too much of a kind of far-fetched thing. Do we use it? We use L for angular momentum, except to avoid the confusion, it's usually the capital L that we use for angular momentum. So this is where you would have seen some kind of L. And I will tell you now, this L is related to this L, but not quite. So let me give you a name for it, if I remember it. Angular momentum quantum number, orbital quantum number. It's one of those two. Let me call it angular momentum quantum number. And your textbook actually gives you a proper name. Let's look it up. What does it call L? All right, angular momentum quantum number. And M has other names other than this, but this is correct description as far as it goes. So, so this L, so by the way, all these quantum numbers, as you can see here, they are usually integer values. That's why we call them quantum number. These are how we quantize different states, different energy levels, but there are physical quantities that's associated with the quantum number. With the N, it's most closely associated with the energy directly. That's where you get this. This is called the angular momentum quantum number because this L is associated with the magnitude of angular momentum of the electron. So imagine if you have proton and electron orbiting around like this, then it has some value of angular momentum pointing in this direction, right? Now imagine it's spinning like this. So it has different value of angular momentum pointing this way, but both this state and this state could have the same magnitude of angular momentum. So both of this state and this state would have the same L, magnitude of angular momentum. And this is the place where Bohr model starts to go wrong because the magnitude of angular momentum is not, well, for one, it's not NH bar. It's not even LH bar. It is some other number. Let me write it down. The magnitude of angular momentum, capital L, is equal to, well, there's a H bar in there. H bar is the unit of angular momentum if it's in there. But it's H bar times square root of L times L plus 1. And I'm afraid that there's no really intuitive way to explain this other than that's the result you get from the mathematics of it. Good? Questions? Good? So this thing that we are assuming, so what about what we are assuming in the Bohr model? It turns out you can still salvage this if you reinterpret this as not meaning the magnitude of angular momentum, but instead the projection of angular momentum. So your textbook calls this last quantum number m. It calls it angular momentum projection quantum number. That's fine, that's a correct description. Let me, I will give you the name and then double check to make sure. The more fancy name for this, which I like better, is called magnetic quantum number. And I actually prefer that name mainly because that kind of ties in better with what we do in atomic, molecular, and optical physics. So this magnetic quantum number actually has a physical meaning. As your textbook says, it's the angular momentum projection quantum number. So this is actually associated with the way we usually arrange the coordinates with the projection along the z-axis. So if you take the angular momentum, take its projection along the z-axis, then that projection takes on the value of m times h bar. So you could say, all right, this n, we actually meant m. We meant a different integer, not n. And we actually meant the projection, not the magnitude. Now, let me point out something that I'm hoping will have you wondering for a while. Let's say you have an electron in some state here where it's orbiting the proton this way. And let's say we have the projection of this angular momentum of the electron so that it measures plus h bar. Good? What would you say the magnitude of that angular momentum is? If electron is spinning this way, so the projection along the z-axis is, it's not actually spinning, all right? So you have a proton and you have some electron formation around it. When you measure projection along the z-axis, you measure h bar plus h bar. What would you say is the magnitude of the angular momentum of the electron in that state? Do you need to know any additional information?
Could you repeat your question?
Okay, so let me draw it here. So let's say, so you have a proton here, and let me just draw electron in some mysterious cloud, right? So I'm not assuming some kind of classical picture. So I have electrons in some mysterious cloud that represents the state of the electron, and you measure the g component of angular momentum. There are different ways of doing it. Let's say you just did it. And when you measure g component of angular momentum, you measure that to be plus h bar. All right? Good. Suppose someone asks you, what is the magnitude of angular momentum of this electron?
If it moves in your plane.
Yeah, so that's why I didn't want to say, because moving in a plane implies a classical picture. Right? So I didn't want to give you the classical misunderstanding. Are there any additional information that you need to know? Like, so you said you wanted to know if it was moving in a plane. How else would you express that idea in terms of physically measurable quantities? That if whatever quantities you want me to measure, I will tell you what your measurement will be.
Direction of the velocity?
Well, velocity is another classical quantity.
Linear momentum?
Linear momentum is, it's quantum mechanical, but because it's around this thing, linear momentum will be constantly changing. That's why we are describing in terms of angular momentum. Let me give you a little bit of help. I think what you're trying to express is the x and y component of angular momentum, right? Because if something is moving only in one plane, then its angular momentum is in one direction, and you won't have any angular momentum in the x or y direction. So I can tell you this, whatever state this is prepared in, Lx, when you measure it, is going to be 0. And when you measure the y component of angular momentum, it's also 0. So I'm asking you for a state that's somehow found that way. What do you think is the magnitude of angular momentum for such a state? Yeah. So this is where your classical intuition will disagree with rigorously derived quantum mechanical result. Because for a state that's characterized this way, your magnitude of angular momentum will be h bar times square root of 1 times 1 plus 1, or this, or I guess h bar times square root of 2. There's no real intuitive way to get at that. What I can tell you is this. So you have, I guess, your intuition has to start from somewhere. So these different values they can take is probably a good starting place. So you will see how, starting with the n principal quantum number, n limits the values that n L can be. And L limits the values that m can be. Okay? So what that means is for n, so if your electron is very close to the proton, then it limits how much angular momentum it can have. In fact, for the ground state n equals 1, what is the largest value L can be? Yeah, 0. So this is actually another thing that Bohr model has wrong. Bohr model doesn't allow for 0 angular momentum state. Turns out n equals 1 corresponds to angular momentum 0. This is the spherically symmetric state, or in your chemistry class, you would have seen like electron cloud that's just kind of fuzzy ball. It doesn't have any other feature other than that. That's your n equals 1 state with the 0 angular momentum. All right. So and with the higher values of n, you can have more angular momentum. That's expressed by additional values L can take. And so L is the magnitude of angular momentum. So in some intuitive sense, the most that the projection can be is plus or minus the magnitude. That's what this limit represents. Now, what I want you to be careful with is for the actual values you would measure, this is the actual projection you might measure, and this is the actual magnitude you would measure from some other set of measurements. And other than to puzzle you, I think I'm just going to leave you there. I'm not going to really explain how that comes to. Your textbook does try to explain it with some figures. I think, is it in this section? Yeah, so it like tries to give this figure, and you can kind of imagine the quantum mechanical angular momentum as this arrow that's spinning around the z-axis. So when you measure the average value of this or this projection, you get 0. But it comes down to there's a fundamental uncertainty relationship between measurement of these three. So it was actually wrong of me to give you an impression that I can prepare a state in such a way that you can have a determined value of LG and have a determined value of these two. You can't. I can only talk about the expectation values of this, which are 0. And so your textbook does try to describe the angular momentum. I have some lab activity in mind, but let me try to work that out for Thursday, and we'll have all of the lab period to start developing some idea of quantum mechanical angular momentum for you. Because I feel angular momentum is one of the truly quantum mechanical concepts. It's one of those things where the first time you see it, you think it corresponds to something you learned in classical mechanics. And the more you learn, the more you realize it's not actually very classical. So I'll try to come up with some exercise for the lab, taking advantage of the 3 hours of time you have for the lab. But for today, I just want to leave it there. 3 quantum numbers. These relate to the angular momentum, magnitude, and projection. And in some intuitive sense, you can kind of relate them that way. Magnitude, it can only be 0 and positive. And projection, it can only be plus or minus the magnitude. But when you go into deeper detail, there are some discrepancies. So that's something for you to be aware of as you get into that. So what I want to do in the next 20 minutes or so
is actually just doing a set of calculations for a situation that relates to this, but isn't gonna be exactly this. It's gonna be a set of calculations that's similar to what you have seen, but it'll be different in some ways. And I'll be able to point out some of the significant distinctions. So I think it's good for me to start by copying this form of Schrodinger equation. So what I should call this is three-dimensional particle in a box. So as a reminder, you know particle in a box. You've seen that before. The 1D version looked like this. You have this box of potential. You had the potential go up to infinity at x equals 0 and at x equals L. The potential is going all the way up to infinity, and you found a lot of wave functions and energy levels associated with them. And the Schrodinger equation, if you remember, that applied to this situation, I'm going to write down just the time-independent version, was minus h bar squared over 2m, double position derivative of the wave function. And for the potential energy part, it had a 0. At least for the region from x equals 0 to x equals L. And we made some arguments how outside of this region, wave function should be 0 exactly. So the whole equation didn't matter. And that's equal to, for the stationary solutions or energy eigenstates, they should have an energy eigenvalue times the function itself. You could also write this in the operator form. Momentum squared over 2m psi x is equal to energy, not an operator for this time-independent Schrodinger equation, times psi x. So this is what you have seen in chapter 7. And this, frankly, was the only example of detailed working out of Schrodinger equation. If you look back for any other scenario, we didn't work it out in detail, even for simple harmonic oscillator. So this is the Schrodinger equation for hydrogen atom. And as you have seen in the textbook and you've seen me cover in the lecture, this is actually fairly difficult, and we're not going to work it out in detail. We just have you do some simple calculations using the known solutions. And really what's causing difficulty in this three-dimensional Schrodinger equation for the electron in the hydrogen atom is really this term here, because this term contains this coordinate variable r. And if you were to rewrite this as square root of x squared plus y squared plus g squared, then you can begin to see that, oh, this is a really super complicated differential equation. So it's going to take heavy machinery of differential equation solving to solve it. So we are not going to do that. What we will do a version of this that is much easier, because what we will do is, okay, let's not do the Schrodinger equation for hydrogen atom. Instead, we'll do a related one that's much easier, one where we can say, oh, my potential is equal to 0. That's what I mean, three-dimensional particle in a box. And if it's just the potential is equal to 0, then that would be a free particle, and that's a whole kind of mass. So let me spell it out exactly what I mean. My potential as a function of x, y, and z, it's gonna be 0 when it satisfies a particular condition. And the condition is that my x is between 0 and L. X. Let me keep that separate for now. And let me put a constraint on my y variable. And I'll worry about the boundary values later. So it's 0 within this box, within this cube of a certain size. And outside of that box, let's say my potential goes to infinity otherwise. So this equation I have written down, it really applies only within this finite region.
that'll make it easier for us to handle it. Kind of similar to 1D particle in a box. I hope a lot of this begins to sound familiar. So this is our starting Schrodinger equation for our particle in a box. Minus h bar squared over 2m. And I'm actually going to do a little bit of a factorization that your textbook doesn't. I'm going to write down a sum of these differential operators. Derivative with respect to x, derivative with respect to y, plus derivative with respect to z. All of them acting on some wave function as a function of x, y, and z is equal to some scalar coefficient times the same wave function as a function of x, y, and z. And only under this condition here. Outside, because the same argument applies. If the potential goes to infinity, then the only way you can make the wave functions come out right is to say for this equation, when it's not meeting these conditions, 0 equals 0 for other x, y, and z. Because so I'm not worried about other values of x and y and z. Other than I guess I should specify that psi of x, y, z is equal to 0 in this other cases. So this is beginning to come to be a place where I can't quite draw full drawings. So I'll have to draw kind of a snapshot cross sections. So for one, as for the kind of spatial distribution, what you have is this. Let me call this my origin. Then this point along my x-axis this point is gonna be Lx. This is gonna be Ly along my y-axis, and along my z-axis, this is gonna be my Lz. Oh, I called it a cube, but I guess technically it's a cuboid? Later on, when we get to the right part, I will eventually set these dimensions to be equal to each other. But for now, I'll keep them as a separate letters so that we have more flexibility as we go. So yeah, that's a kind of a figure of the region within which we have an interesting wave function, as in our wave function is not guaranteed to be 0. And you can already see that we are running out of space here. I've already used one axis more than I have in drawing the region, so I don't have any axis to indicate how my wave function looks like. So I think for this lecture, I will limit myself to drawing one-dimensional projection of the wave function. So that I can actually sketch both of the coordinate variable and the values of psi, because yeah, I already have 1, 2, 3, 4 parameters I might sketch, so I have to pick 2 somehow. So if you're staring at this and don't know quite where you would go, you would be in good company. Because I think you might recall back to your solutions for one-dimensional case. So you think maybe something like this might work. You say, okay, psi of n x. This was my set of my solutions to the one-dimensional particle in a box. I think this was sine of pi x over L sub x. So with this solution, I think the differential equation is satisfied as long as you can say that my values of my energy, oh wait, I forgot n here. It could be potentially n pi x. As long as my values of energy are n squared, pi squared, h bar squared over 2mlx squared, then this was allowed the solution. So now if you're thinking of trying this out just here. I think it might actually work. So it does, if you are, so since this is a form of solution that you are familiar with, if you just to try this, I think it actually works out to some degree. It seems to work out until it doesn't. So let me show you how it seems to work out and show you how it doesn't work out. So let me just plug this in. If you plug this in here, this is what you see. You have minus h bar squared over 2m. And I'm just going to replace these derivatives with what you get when you take the derivatives. You get what I was describing earlier, minus those two factors that you get from chain rule, m pi squared over lx squared, and squared pi squared over lx squared, and you get a times, I already wrote down the minus from, derivative sine is cosine, derivative cosine is minus sine, so sine of n pi x over lx. Okay, that's my x term, and my y and z terms are super simple. This is a function that does not depend on y and z. These partial derivatives, the explicit instruction is for you to treat everything other than y and z as constant. So, this is 0. This is also 0. Okay, we are done with the left-hand side. So you write down the right-hand side, e times, let me just write out psi of x, y, z, technically just only psi of x, a times sine of n pi x over lx. So you think, hey, this looks exactly like my one-dimensional case that I was looking at earlier. So it looks like it's all gonna work. So you say, my wave function solution is this, and if you wanted to, you can do something similar for the y direction. You say in the y direction, this is a sine of m pi y over ly. For the z direction, you say a times sine of n pi z over lz, and you say, oh, I'm all done. I found my 3 solutions, and I can put in any of these in here, or I can put linear combination of these here, and it'll all work out. As you are, as I'm saying that to myself, here's a reminder to always do this. You have to match boundary conditions. And what you will find is that for each one of these solutions, 1, 2, and 3, they can only match boundary conditions for one of the dimensions, the dimension that they have the variable for. I mean, that's how the one-dimensional solution was built. So for this x dimension, the boundary conditions are matched. But for example, take this y dimension solution, for example. Not only this needs to satisfy the boundary condition that at y equals 0 and at y equals L of y, L sub y. So at these values, you need to have psi of y equal to 0. That is satisfied. That's one of the boundary conditions. But the other boundary condition is at x equals 0 and at x equals L sub x, my psi of y has to be equal to 0. And that cannot be satisfied. For example, take the point where x is equal to 0 and y is equal to ly over 2. Then this sine of y, that's going to give you 1. And at this coordinate point, this is not guaranteed. So these solutions that I was proposing, they cannot be used to match boundary conditions. So you cannot propose any one of these individually as a possible solution to this three-dimensional Schrodinger equation for the particular scenario we are working on. So you might say, okay, we've seen this problem before, and I kind of alluded to it when we were doing the one-dimensional particle in a box. I did say something about how the free particle solution that goes infinitely in both directions is it's not physically possible solution, but you can kind of use them to build up your physical solution. So maybe you try something like this. Okay, let me give them separate labels X, Y, and Z. And you say, okay, so my wave function needs to depend on all X, Y, and Z. So my problem before in trying to match boundary conditions was that my wave function depended only on one of the three coordinate variables. So you say, okay, I'm gonna use this to build up my combined wave function, and you build up something like this: a sub x sine of n pi x over lx plus a sub y sine of n pi y over ly plus a sub t sine of n pi t over lt. Now, if you are considering if this might work, you'll find that it doesn't work. Because I think I can demonstrate this really simply this way. So when you have a boundary condition that says that at the values of t is equal to 0 and L of 0, you need to have your total wave function equal to 0. This is a condition on only one of your three variables. So, I mean, you could do all you want to make this equal to 0. That you can definitely do. In fact, this is built to exactly do that. But here's the problem. What this boundary condition means, whenever this is met, for all values of x and y, this also needs to hold. And that doesn't happen because 0 plus non-zero values here, that's non-zero. So this particular linear combination of wave functions won't give you what you're looking for, which is a total wave function that can actually meet these boundary conditions. So I guess there are two different ways to get at the actual solution. How do I introduce in a minute or so? One is to say, to kind of keep doing what we've been doing so far, which is just guessing and checking. We don't have any experience with any of this. It's no shame to not get the correct answer at first try. So we tried guessing plus, that didn't work. We could guess times. We could guess that what if we multiply them? Will that work now? We can do that. It'll turn out that it'll work. So that's one way to do it. And I find that slightly unsatisfactory. So let me try to give you a little bit of a mathematical explanation why this way of combining solutions will actually give you an answer that'll work. As in, it satisfies the Schrodinger equation, and you can use it to match boundary conditions. I think being able to match boundary conditions, that's the easy part to see, because once there are products, then once you can make, and given that my boundary condition really amounts to making psi of x, y, and z equal to 0 as some correct coordinate values, this product arrangement really makes it easy to make the wave function go to 0. If any one of these three factors are 0, then the whole thing is 0. So I think that part is really easy to see. The part that might not be all that easy, particularly because most people in this class won't have experience dealing with a partial differential equation, is how would this be a viable solution to this differential equation. I mean, I'm just multiplying stuff together. And I think you are used to seeing linear combination of solutions being a solution, but this is not a linear combination. This is a product of solutions. You have no reason to expect, for example, this solution one times itself, that's not a solution. So I think that's the place where you need a little more justification why this particular combination of solution would be a solution. And this is what I am referring to in my keywords as separable solutions. So let me copy this over and illustrate what's meant by separable solutions. All right, so separable solutions idea starts out with this supposition. So it's not that you necessarily know what the exact actual solution is, but not knowing the actual form of the solution, this whole multivariable function, I know it's complicated without actually having attempted to write it down. So my sincerest hope is that I can write down this multivariable function in a way that it can be separated into discrete chunks of single variable functions. And one way I'm hoping it might be able to be separated is one function in terms of one variable times another function in terms of another variable of the three times another function in terms of another variable. So, I have three variable, multivariable function. What I'm supposing is it is possible to divvy up this solution in this way. Let's see what happens to this equation. I'm going to, let me just plug it in and just write down what happens. I guess I'll write it in green. So I have minus h bar squared over 2m. Let me keep the order careful so that I can clearly see what's being differentiated and what's not. So as this differential operator is acting on the wave function, with respect to y and z, it's not going to do anything. So this is going to move right across the derivative operator. So I have basically scalar multiplication by these functions times double derivative with respect to x. Be careful here that this is capital X, this is lowercase x. Let me keep going. With here, it's the other two functions, the function in terms of x and z that moves through the derivative, and I can treat that as just a multiplication by scalar, and I have the double derivative with respect to lowercase y. Same deal with the last term. The two functions that can just move right through the derivative operator and the double derivative with respect to lowercase g. So that's what I get when I apply this here. And that's equal to some scalar times the whole wave function x, I guess, y times t. And you might look at this and think, hey, this doesn't look any simpler. What am I doing with this? Let me do something that I can do, because I used to have a quantum mechanics professor who used to say, because you can't stop me. Because, I'm doing a perfectly valid mathematical operation. You can't stop me from doing this. I'm going to multiply both left and the right hand side by 1 over x times y times g. The places where they go to zero, yeah, I'll deal with that. Those are pointwise singularities. But for the most part, I can just do this. And let me write out the result of this operation. When you write out the result of this operation, this is what you get. Minus h bar squared over 2m. For this first term, you see y and g cancel out, and I just have this x left. So I have 1 over x times this double derivative plus something very similar here happens. All but one of the functions cancel out. So the 1 over y as a function of y times double y derivative of capital Y plus the same deal with the third term, 1 over the function g times the double derivative of capital G with respect to lowercase g is equal to some number, scalar e. And when you look at this, this is the argument that is made. The quantity on the right-hand side, this is constant. And that's actually quite remarkable, because when you look at these three terms on the left-hand side, you have a function that function entirely over a single function. And if you look at the second term, that's again a function. I'm just making up letters. Function of an entirely single function. When you look at this is again a function. Oh, what comes after theta? Oh, phi theta. Oh, I don't know. Capital psi. Sorry, this is a very confusing letters. What I'm trying to say is that this is a function of a single variable, function of a single variable, function of a single variable. And for these two each add up to a constant, really the only way this can possibly happen if this is constant on its own, and this is constant on its own, and this is constant on its own. Because if that weren't the case, then you can imagine, if two of them were constant and this last term wasn't constant on its own, then you can just imagine varying the parameter g, and this whole thing would have to change. And the fact is, it shouldn't, it can't. That's the constraint here. So what this is showing is that this individual, each dimensional term individually has to be constant on its own. So that allows you to basically separate out this Schrodinger equation, where this right-hand side, instead of this looking like a single scalar times the wave function, you can kind of look at this as, so you can go through the detailed algebra to justify this fully. What this is going to look like is the constant scalar that's associated with one of them here is sub x, plus the constant scalar that's associated just to one of them here is sub y, plus the constant scalar that's just associated with one of them is sub g, times the entire wave function again. So this is what we refer to as separable solution, or rather specifically, this is the separable solution. And this is by no means no constraint that all the solutions to this wave function has to be separable. It might not be. This is one set of solutions that we can easily find, with which you can build up any other more complex solutions. And the nice thing about the separable solutions is that each of these components of the solution, it's a solution to the one-dimensional version of a Schrodinger equation, where we say this term is equal to E of x, this term is equal to E of y, this term is equal to E of g. So this procedure allows us to separate out of the three-dimensional Schrodinger equation, each one-dimensional piece at a time. And that's what you see up here. When you go through this separable solution, what you see here is that separated solution. So this is psi n x of x. This is psi n y of y. And this is psi n g of g. And the normalization coefficient, there's no reason to have three of them. I can kind of combine them all into just one for the entire wave function. The whole wave function is normalized altogether. They're not normalized one dimension at a time. So I'll just keep this as A in the front. And this wave function has three quantum numbers, nx, ny, and ng. And you can see from here what the allowed values for the total energy will be. You can kind of generalize from this one-dimensional case, and knowing from having done this separable solution procedure that the total energy will be just sum of the energies. So kind of taking the Q from the solution for the one-dimensional version, you can get something like so energy of the state that specified by the three quantum numbers nx, ny, nz is equal to the sum of this with a version of the x, y, and z. Let me just write it out. I'm gonna factor out the part that can be factored out, pi squared h bar squared over 2m times, and this is the part that can be factored out, nx squared over lx squared plus ny squared over ly squared plus ng squared over lg squared. So that's it. That's kind of the solution to the three-dimensional particle in a box Schrodinger equation. And there are a lot of interesting things you can explore with this. One is the idea of what you might call energy degeneracy. And you've actually seen that with a hydrogen atom. So with the hydrogen atom, when you are looking at the gross structure, the principal quantum number gives you the energy level. And when you change the angular momentum quantum numbers or the magnetic quantum number, it doesn't give you a different energy. So you have what we call degeneracy in energy levels, as in distinct quantum mechanical states have the same energy. So given one energy, there are multiple wave functions that match to that energy. And the way this is written, you can't quite see that, but if you were to consider a special case where the box is a cube, then you can see that you do have that degeneracy. So for example, 2, 1, 1 state has the same energy as 1, 2, 1 and 1, 1, 2 state. So and those three states characterized by three different set of quantum numbers are different states, but they have the same energy. And this kind of degeneracy is something that's impossible to see in the one-dimensional case, and you really need to deal with the multiple dimension, 2 or 3 dimensions or higher, to see that degeneracy in energy. So that's one. And the other, I wanted to talk about uncertainty principle and operator commutability. What that amounts to is what I actually kind of used without pointing out explicitly. So when I was working out this expression here, I kind of commuted these functions in terms of y and z with this momentum operator for x. And same deal here with the momentum operator for y. Same deal here with the momentum operator for z. And so, you have seen the uncertainty principle in this form. Delta p times delta x, uncertainty, momentum, and position is greater than or equal to h bar over 2. And it turns out what's important here, this is only for the uncertainty momentum in the x direction. So if you are, for whatever reason, looking at uncertainty in the momentum of y direction times the x position uncertainty, for example, that can actually equal 0. There's no prohibition. And this boils down to mathematically that the measurement operator for x, which is multiplication by x, it commutes with a measurement operator for the momentum in the y component, which is proportional to the derivative with respect to y. These two commute, they can swap the order without affecting anything. So, so there is no such uncertainty principle like this with respect to operators combinations like this. So, and that's also kind of something that we talk about more in upper division quantum mechanics. In lower division quantum mechanics, we don't have the necessary tools of linear algebra, the upper division level linear algebra. So we'll leave that there. So
So let me show you how we draw level diagrams. You've actually seen some of this already. I think your lab manual actually had this level diagram. So this is how we represent energy levels in an atom or in a quantum mechanical system. And let me point out something that I didn't explicitly point out yet. Looking at this description here, so any given state, you can specify it with these three quantum numbers, N, L, M, right? So if you have N equals 1, that's kind of it. That's the only state, because the only allowed value of L is 0. So, and the only allowed value of M is plus minus 0. So that's the only allowed state. That's all fine. Things get more interesting with the higher values of N. Because with the higher value of N, if N, L, M are all right, so let's say N equals 2, then now you're beginning to have some possibilities. You can have 0 for L, in which case we will continue to have boring 0 for M. Or you can have 1 for L. Then what are some possible values for M? Minus 1 plus 1 and then 0. Yeah, so going in order, minus 1, 0, plus 1, right? 3 different projections. Good? So in other words, once you have N equals 2, then there are total of 4 distinct states that you can solve for. And what we mean by 4 distinct states are 4 distinct wave functions. So different value of L corresponds to different value of different radial wave function. And different value of M's corresponds to different spherical harmonics. So that's what those distinct states are. How many different values of energy do you think are there for those 4 different states? 4 as in 1 plus 3, 4 different states. So the question is, so here we had only one state. So all right, that's it. I guess we're fine. I'll leave it there. So we have one state here. And here, starting with N equals 2, you can have 4 different states with N equals 2. Right? And for each of those states, we can imagine measuring the energy of the electron. What do you think is the energy of the electron in this N equals 2 state? Like you're looking at this formula here, right? Right? Does it seem to depend on L or M? So what that means is these 4 different states, they all have the same energy. They all have that value of energy, or minus 13.6 divided by 2 squared. These are what's called degenerate states, or they call it degeneracy, where multiple states have the same energy. This is something new. You can only get degeneracy when you have more than 2 dimensions in your problem. With a 1-dimensional setup, you will never get a degenerate state. If 2 wave functions look different, they also have different energy. So one way of conveniently illustrating, like diagramming all of this, that these different quantum numbers and the fact that some of these states have the same energy is the level diagram. So let me just draw an example of energy level diagram so that we're not just talking in vacuum. So level diagram. Oh, I didn't look ahead of time where in the textbook this might be drawn. It's kind of a simple diagram. Let me draw mine and maybe I'll look for it if I feel there's time. So I guess with the hydrogen I can do this. I can say this is where n goes to infinity. Or this is the reference where energy is equal to 0, eV. Right? Yeah, I can't do this with infinite square wall, but with hydrogen I can. And the very lowest energy state is, so this would correspond to E equals minus 13.6 eV for regular hydrogen. So E1, 0, 0 is equal to minus 13.6 eV. So I'm going to only draw the next two values of n. So the next level up, it's kind of a bit out of scale. I'll just draw it here. So this, let's say this stands for E200 is equal to minus 13.6 eV divided by 2 squared. And this will be the same value of energy for E210, 21 minus 1, 21 plus 1. So I'm going to draw them all this way, kind of more or less on top of each other. The wave function 210, zero projection along the axis. And then I'm going to have two different states to the side. So this would be where m equals plus 1, m equals minus 1. Yep. Let me draw just one more. So the next level with n is n equals 3. So with n equals 3, I have this state. So so I guess psi 3, 0, 0, that's still a possibility. You can have zero angular momentum, like 0 everywhere. And L equals 1 is still a possibility. So you can have that. So psi 3, 1, 0, and then these two different projections on either side. And now you can have one more level of L. You can have, so I kind of need to draw it right on top of each other. Psi 3, 2, 0. And there's also right on top of that. So I guess there's, because I'm trying to draw degenerate states, they all look kind of bunched on top of each other. So this is one way of drawing it. You can kind of see the organization scheme. So I guess it comes down to you have 3 parameters. And if you're doing this on paper, you only have 2 dimensions. So you kind of have to pick the 2 that you're going to illustrate. I've chosen to pick n and m. So this axis represents n equals 1, n equals 2, n equals 3. And this axis here represents m equals 0, minus 1, minus 2, plus 1, plus 2. So that's the choice I made, and that's one way of kind of doing the energy level diagram. And this axis here is being used for energy. And what I'm trying to illustrate here is that you have these different energy levels that, well, you have these different states that have the same energy. So as you get to higher, more excited states, the number of states that have the same energy increases and it becomes more complex. So here's a question that you should reasonably ask. If all these states have same energy, like why are we even calling them different states? Why aren't we somehow kind of, collapsing them into one state? Like what's the distinction between having m equals plus 1 and m equals minus 1? Right? Yes. And that's where it's because these are actually physically distinct states. In an experiment, you can do something to lift the degeneracy. You can do something to make it so that these states end up with a different amount of energy. So this is the energy that they would have in their natural, undisturbed hydrogen state. If it's in isolation in vacuum chamber somewhere, no one's doing anything to it, then that's what this looks like, roughly. But if you start, for example, applying magnetic field, the electron will begin to interact with the magnetic field, and that will start to cause these energy levels to change. This m plus 1 state, if you're applying positive magnetic field, then I think this, I need to make sure I remember this. I think it goes down, and this goes up, and this state remains the same. So with the application of magnetic field, you can split this degeneracy. One energy level goes down, another level goes up, and the effect that describes this is called Zeeman effect. And I guess I kind of want you to describe this in detail, but I have 20 minutes, and I'm not sure if it's worth that 20 minutes. Let me point to you in your textbook where you can read about it. I don't know if your textbook calls it Zeeman effect, but let me point to you in the textbook where you can actually read about it. So yeah, it's not here. I think it's the immediate next section. So, oh yeah, these are pictures of electron clouds that you may have seen. So let me go to the next section. Well, that's not technically correct. I'm more familiar with the ground states than anything. By the way, so if I make you do any calculation with the hydrogen atom, it'll usually be with the ground state. I will give you the wave function, I'll give you some simplified form, and you will be given kind of exactly what to calculate. It'll be integral exercise if you get any calculation in this class involving hydrogen atom. All right, so this is where it actually requires a fair amount of time. That's why I'm just pointing you to the section of the textbook that covers it and not actually showing you. It has to start with a review of magnetic dipole moment. Current times area of the loop. I don't think I really spent that much time on magnetic dipole moment. It's something I'm planning on fixing next semester. So yeah, you have to read about it. Review it, and magnetic dipole moment. And there's the interaction with the magnetic dipole moment with, or dipole moment with external field. It's a lot easier to drive that interaction with electric dipoles than magnetic dipole. But if your physics 4B teacher did a proper job, then you would have covered at some point potential energy of a dipole in an applied field. So that's the torque. Potential energy of a dipole in an applied field is this. So when a dipole points in the same direction as the field, you have lower energy. And this is what leads to this shift of energy levels. And let me see if your textbook actually calls it Zeeman effect. Yeah, here, Zeeman effect. And the effect of this Zeeman effect is that these energy levels split. So where they used to be at the same, I guess so they are plotting the transitions where they used to be, so this L equals 1 to 0 transition, it's actually potentially 3 different transitions because it's either, so either from 4 different transitions, subject to a selection rule that might rule out one of them. Actually 3. So with the psi 210, you have this state from here to here, 1, from here to here, another, or from here to here, 3. With the 0 applied field, all those 3 transitions show you the same energy. But once you start applying magnetic field, and if you have enough resolution to see it, then you will start to see that spectral line split. This transition will now involve lower energy. This transition will now involve higher energy. That's what this splitting here is showing. And when people do the experiment, they can see that this splitting is linear in the applied magnetic field, consistent with the DC here. And if we are dealing with a state that had a degeneracy of 5, as in 5 different states, then you see the line splitting into 5. So that's how you could know experimentally that there are really 5 different states. Under an applied external field, it behaves differently. Yeah. So you can read about it in detail here. I think your textbook gives you good enough of a background. And just as a matter of personal background, the atomic physics group I was in, a lot of our work was actually involving this. It's it's a more other version of it, but essentially we were using Zeeman effect to measure magnetic field. And it's a little bit different than visible light spectroscopy, but it's what it boils down to. So the reason I want you to save about 20 minutes was to talk to you about something that's purely quantum mechanical, for which you have no real analogs and no real classical comparison to compare to. And I haven't read your textbook section yet, but it ought to relate to where it covers electron spin. It ought to relate to that, bit about it. But I want you to talk to you a little bit about more abstract consideration that we haven't actually even mentioned yet. So the thing that we haven't even mentioned yet is all these wave functions that we are talking about. How many particles are we describing? Just the one, right? In fact, do you remember us dealing with more than one particle in any bound state consideration? No, right? When we were dealing with the infinite square well, it was still one particle, hydrogen atom. In fact, the reason we only talk about hydrogen atom and never helium atom is that helium atom has one too many electrons. We can deal with one. Two is a little bit too many, so we don't really deal with that. But I mean, but helium atom exists, so there are some considerations we have to deal with. So I guess it's probably easier for me to just give you the conceptual idea in the context of infinite square well of non-interacting particles, as in we assume that these particles have zero charge. So let's say you have an infinite square well. So I want you to ignore for now, if these particles have zero charge, how am I confining them to a square well? But ignore that for now. So if we have a single particle, then you know what kind of state this single particle can have, right? You've seen this before. Psi n is equal to some normalization constant times, so let me define my coordinate axis. X equals 0 here, x equals L here. That's just A times the sine of L, pi x n pi x over L, right? Remember that? Yes? What if, so the question is, all right, so that's one particle in an infinite square well. What if we have two particles? I mean, you could say, all right, the second particle here, I think it's going to be described by the same wave function. Psi of n2 is equal to A times the sine of n2 pi, I guess, x2, position of that particle, over L. Like that probably would describe that particle, right? Yeah. Now here's the question. What if I want you to describe the whole system? What if I want you to describe the whole system in a single wave function? Psi of position of particle 1, x1, and psi of x2, position of particle 2. And this is something that you wouldn't know the intuitive answer to. The mathematical procedure for doing this, describing a multi-particle system, is actually quite simple. It's taking these individual particle wave functions and you just multiply them together. This is simply equal to psi n1 x1 times psi n2 x2. That's it. Separable solution of, I guess the way you imagine doing is you first write down the Schrodinger, multi-particle Schrodinger equation, and this separable solution is the solution for that multi-particle Schrodinger equation. So it's pretty simple, right? You can deal with the multi-particle systems this way. Yeah? Now, this is where some people thought about this for the correct amount of time and thought about an issue that was really never an issue in classical mechanics. So imagine you have these two carts. So I'm still dealing with a two-particle system. And so these two carts are somehow interacting. You know what? I probably should get a track. I'll be right out. So, all right, I have two carts. So suppose these two carts are interacting here. One cart comes in, collides, another cart goes out, right? So would you say that, let's call this cart 1, cart 2. Would you say cart 1 came in and then cart 2 went out? Like, how do you know that? So imagine it from experiment. So I guess one way you can say is, I'm looking at it. Cart 1 came in, stopped, cart 2 went out. Now, you know that kind of thing is not realistic in quantum mechanics. You cannot constantly observe something because then you are constantly disturbing it, you're constantly affecting its state. So, you can't do that. You can make measurements at some particular intervals, just not constantly. So let's say one snapshot that you observe is a cart 1 coming in, and another snapshot that you observe is one cart going out. How would you know that it was cart 2 that's going out?
Because initially it's stationary in the first.
So if you are making those, how do you know this didn't happen? If you closed your eyes for 2 seconds, so you saw this card coming in, and you saw this card going up, but in the meantime I lifted this and put it back in, so they never actually interacted. Like, how would you be able to figure out that that didn't happen?
Would it change in your mathematics?
No, so I mean, imagine this. Okay, so look at this snapshot, and okay, snapshot 1, snapshot 2, 2A. Compare that with snapshot 1. And snapshot 2B. Snapshot 2B looks pretty much like a snapshot 2A if you're looking at momentum and energy. Like, we're talking classical mechanics. So in classical mechanics, what would you do to make sure that you can figure out, is the outgoing cart 1 or cart 2?
Label it.
Yeah, you would label it. So in classical mechanics, that's the underlying assumption that two objects, you could say that they have the same mass. You could say that they are identical, but at some point they are distinguishable. The assumption is that you can always, all right, call this cart 1, call this cart 2. And no matter what I do, now that you have labeled it, you can tell if I did this. Because you will see, oh, it's my cart 1 that's going out. So this assumption that you can always label things breaks down when you get into microscopic world of quantum mechanics. What would you label electron with?
Spin.
Now, spin is a property that can change, right? Spin of just like momentum of a cart can change, spin of an electron can change. It can, spin up or spin down. It can flip through interaction. So what would you label the electron with? You don't need, so when doctors trace particular chemicals, how they are metabolized through your body, they tag it with isotopes. So you need something smaller than an electron to label the electron with, and you don't have that. So this idea of totally, completely indistinguishable particle is a purely quantum mechanical idea. And it's an idea that has to be taken seriously. So this is what it means. When you have total wave function like this, it needs to obey a particular kind of exchange symmetry. Meaning, if I swap the particle identities, so in this particular case, what that would mean is I take this number here, position of particle 1, I swap it with this here, position of particle 2. So if I wrote this, psi n1 x2 times psi n2 x1, this has to be equal to this. So the idea that this is a condition that must be observed is exchange symmetry. And this is a foreign idea to classical mechanics. Like, why would you expect that? But in quantum mechanics, where in your theory you build in the fact that your particles are indistinguishable, this is a reasonable requirement. That unless your wave function didn't change when you did this, then like something's wrong with your theory. Like it's like this is a symmetry operation. It's a symmetry operation like rotation, mirror, translation. So it's a symmetry that must be obeyed. And now when you look at this general function, I mean, this is obviously not true. They look different. And when I actually put in the actual function forms, that also looks different because n2 times x2 is not, n2 times x2 is not equal to n2 times x1, right? So even though this is a way to build up a multi-particle wave function in general, when you start thinking about the fact that the quantum mechanical particles are indistinguishable, this starts to break down. And you need to have a way of constructing wave function so that your wave function obeys this exchange symmetry. Let me show you one example of that. I can actually use this as a starting point and build you this symmetric wave function. So let me, all right, I'm staring at this and I have some ideas. Let me try out that idea. This is what I'm going to propose is my symmetric wave function. x1, x2 is equal to, well, so my problem is that when I swap these two, it becomes an entirely different thing, right? Let me try it this way. Psi n1, x1, so it's the same thing. Psi n2, x2. And then I'm going to add this to something that will help the overall thing become symmetric. Plus psi n1, x2, psi n2, x1. Does this have, is this symmetric under particle exchange? Right? Because when I exchange, this becomes that, and this becomes this. So the overall sum is symmetric. So this is a wave function that obeys exchange symmetry. This is a symmetric wave function. All right, while we are on this, let me show you one more thing. I can build what's called an antisymmetric wave function. So let me just write out what my antisymmetric wave function is. So this is my antisymmetric wave function. I mean, it might, it's poorly motivated why I'm doing this. It's because I want to explain something. This is my antisymmetric wave function. Psi n1, x1 times psi n2, x2. And this time, instead of adding, I'm going to subtract psi n1, x2, psi n2, x1. Can someone explain what I could possibly mean by antisymmetric?
Odd function.
Kind of like odd function, where, so it's sort of like when you take this antisymmetric wave function and you take it through a particle exchange. It's kind of a complicated operation, right? Change x1 to x2, x2 to x1. It's not just flip the sign. When you do particle exchange, you get minus of that wave function. So just like all the function is a kind of a symmetry to a function. Not every function is even or odd. There's functions that are neither even nor odd. This is two different kinds of symmetric wave function. Even kind of symmetric or symmetric, odd kind of symmetry or antisymmetric. So antisymmetric wave function is kind of almost as symmetric as this because we have this convention that what physically matters is the wave function absolute value squared. Right? So when you do particle exchange, and if the only thing that changes is the sign, then nothing that matters actually changed. That's why antisymmetric is also considered a kind of symmetric. And this is where, with 1.5 minutes remaining, I want to mention the terms of two terms that you may have heard before. The idea of fermions and bosons. How many here have heard the phrases fermions and bosons? Okay, not enough of you. These are just the names. I can tell you what distinguishes fermions from bosons. This is not something I can derive. I just have to tell you. The symmetric or the symmetric exchange symmetry, this is obeyed by bosons. The antisymmetric kind of symmetry, exchange symmetry, this is obeyed by fermions. But that's not the actual definition of a boson and fermion. Boson and fermions are distinguished by their spin. So I guess I'm running out of time, so I'll just give them the English description, and we'll talk about them more probably on Thursday, maybe in the lab. Bosons have what's called integer spin. That means the magnitude of their spin is an integral unit of h bar, like h bar, for example. Photon is a boson. Photon has an integer spin, h bar. Fermions have what's called half integer spin. So most common example of the spin is, I guess this is the kind of spin version of L, is h bar over 2. It's kind of weird. L can never take half integer values. Spin can. And it's kind of because spin is a quantum mechanical thing for which there's no classical analog. So electron spin comes in half integer spin. So electron is a fermion. And finally, here's why this matters. When you look at the whole symmetric versus antisymmetric wave function, imagine that these are your quantum numbers, n1 and n2. When you look at the symmetric wave function, is it okay for you to have n1 equal to n2? Is that okay for your symmetric wave function? Right? All right, n1 equal to n2. So n, oh, so I guess I get 2 of this, right? So, all right, that's fine. So if you have bosons, two indistinguishable bosons can share same set of quantum numbers. Look at the antisymmetric wave function. What happens if n1 is equal to n2? Yeah, if this is n, oops, they cancel each other out. So fermions, two indistinguishable fermions, cannot share the same set of quantum numbers. And this is the reason behind what you've been taught as the Pauli exclusion principle in chemistry. And this is the more fundamental reason for it. There's still a bunch of pieces that I kind of glossed over, like, you know, what are these and why they are defined this way. That requires relativistic quantum mechanics to explain, so that's more graduate level quantum mechanics, even I don't fully understand. So I won't get that far. But this is the more fundamental reason behind the Pauli exclusion principle. Why no two electrons in an atom can share the same set of quantum numbers, because electrons are fermions. That means they obey antisymmetric kind of exchange symmetry. That means their quantum numbers cannot be the same. Yeah. This is something you would cover in chemistry as you're doing electron configuration, I don't know, electron orbitals or whatever. So let me just kind of show you how this pattern that chemists have noticed before development of quantum mechanics is now explained by quantum mechanics. So these are some key concepts that I would remind you of from last week. The number one thing are the quantum numbers. So you can kind of begin to see how these quantum numbers match up with these things that are kind of labeled here. So let me just start writing down numbers, and then we'll make a better physical connection. So for this hydrogen atom, so let me write down these quantum numbers in this format. In the tuple of 4 numbers, tuple? Yeah, 4 tuple, N, L, M sub L, M sub S. So for hydrogen, the set of quantum numbers that characterize the hydrogen would be 1, 0, 0. What should the M sub S be? Not 1. We only have 2 choices, plus 1/2 and minus 1/2. It's either one. Doesn't really matter. So let me leave it blank for now. What about helium? Yeah, for the helium also, it's still 1, 0, 0. So we are still in the same orbital. We are still in the state that's characterized by the same set of first 3 quantum numbers. It has the same principal quantum number, same orbital angular momentum of 0, same the projection of angular momentum of also 0. So really what distinguishes helium and hydrogen is it has more than 1 electron. With the hydrogen, you have a single electron. So you are just, so let's say you have an electron that has a state of plus 1/2. That's the spin, that's fine. With the helium, this is where I have to remind you of Pauli exclusion principle. Everyone remember Pauli exclusion principle? Yes? Kinda? Kian, what does the Pauli exclusion principle say? Don't remember, okay. So this is, where do I want to write it down? Then I think I need more space, so let me write it down here. Pauli exclusion principle. We didn't talk about this a lot last time in class. Last time meaning Tuesday, I think. But we went over the indistinguishability of particles and symmetrization requirement. Symmetry upon particle exchange, because when you have 2 electrons, those 2 electrons as in helium atom, those 2 electrons are utterly indistinguishable from each other. So your wave function description of them has to reflect that fact. That means when you swap those 2 particle labels, then it has to be, in some sense, be symmetric. Yes? Ring a bell? Okay. And of all the particles in the world, we put them in 2 categories, bosons and fermions. Fermions are the particles that have spin 1/2, are fermions. And fermions obey the kind of statistics. In a way, they obey the anti-symmetrization requirement. So let me call it fermion anti-symmetrization requirement under particle exchange. And this is this is the fundamental reason that leads to Pauli exclusion principle, which you may have been just given as an, I don't know, experimental fact in chemistry. And I mean, this is not all that much better because I'm giving you all these principles as kind of like word from heaven on high. So not something you can prove because we can't prove it. But so I just want you to know that there's a more fundamental reason where Pauli exclusion principle comes from. And if you happen to go to physics graduate school, do particle physics theory, then you will see why fermions obey this requirement. It all comes down to what kind of spin they have. The spin is one of the fundamental characteristics of a particle. So, but let me just give you the statement of Pauli exclusion principle. That's what matters for us. Where it comes from, you're not really going to be tested on that. So this is the statement of Pauli exclusion principle that you can use. For half integer spin particles, I'm just spelling out what a fermion is. And in our case, we are dealing with the electron, which is spin half. But I'm saying this to cover the possibilities of spin 3 halves, 5 halves, 7 halves. This covers all of that. For half integer spin particles, no two identical particles. So if you have an electron and I don't know, muon, then you don't care about them. They are distinguishable. This doesn't apply. But this applies when you have two same particles, two electrons. No two identical particles can share the same quantum number, same set of quantum numbers. This is, I guess, so no two identical particles, that's the important part, and the same set of quantum numbers. I think that's as succinct as I can make it. So that's the Pauli exclusion principle. And once again, going back to this, it's because if they share the same set of quantum numbers, then when you try to anti-symmetrize them, you'll get zero wave function, which means you have nothing. So this is how this Pauli exclusion principle applies to the elements you see here. So for helium, you know it has 2 electrons because it has 2 protons. Well, let's say you do know somehow it has 2 electrons. Maybe you've seen it ionized twice. Then, so you say for the first electron, you feed it into the same state as you did for hydrogen electron. So you say, for helium, if I have 2 electrons 1 and 2, let's say for the first electron, based on the kind of energy levels you see, n has to be 1, and that kind of constrains you to having L equals 0 and m sub L equal to 0. Same thing for the second, same thing for the second electron, 1, 0, 0. And for the first electron, let's say for the fourth quantum number, you had it in the spin-up state, plus 1/2. Then for the second electron, it cannot also have plus 1/2. Then 2 electrons are occupying the same state. That's not allowed. So the second electron must have minus 1/2 state. Okay. And this explains why starting with the third electron, you are no longer on this first row. Why? Starting with the third electron, you must go into the second row here because the first 2 electrons filled up these 2 states. And then, so there's no more states starting with 1, 0, 0 that we can fill up because we've used up both of these 2 possibilities. So for the third electron, it must go into n equals, n equals 2 state. Any guesses on the values of L and m sub L? Yeah, it starts out with a 0 for now. So 2, 0. It turns out that the angular momentum does affect the total energy a little bit. So having angular momentum of 0 makes the energy slightly lower than otherwise. So it's 2, 0, then it's 0, then all right, plus 1/2. I'm only writing, so this is the state for my third electron. And you've actually, if you took chemistry, you did this in a different notation, something called the spectroscopic notation, or no, that's not right. Electron configuration. So, I don't know. It's been a long time since I did the chemistry. I don't know if I remember all this. So the electron configuration for hydrogen would be, no, I don't think I remember it. Is it 1s? So hydrogen, it's a superscript 1, right? Okay, for helium, it's a superscript 2. And for lithium, then it'll be now 2s, and then superscript 1 would be for lithium, right? Yeah. Yeah, and so for beryllium, it's still in L equals 0 state. Because for beryllium, I can fit in another, so I have 4 electrons. I can fit in 4 electrons with the 4th one being in the other spin state that I haven't used yet. So for beryllium, this will be 2s2. Now, you jump across this gap to get to boron. Because it's now you've used up all the orbital angular momentum 0 state. So starting with the boron, you have to be starting with here. You have to be filling up 2, 1, and I'll just group this entire set. They span the range of plus minus 1, 0, combined with plus minus 1/2. So 3 possibilities here, 2 possibilities here, so total of 6 possibilities here. Okay? So for these, if you are using the electron configuration notation, chemistry comes with a lot of history. Use letter P, and it'll start with the P superscript 1, 2, 3. Do you write 2 again in front? You do, okay. So, okay, 2P, so 1 through 6 for that. So now that we've laid out, so let me just kind of clean up this notation a little bit and kind of try to organize how these quantum numbers that we are giving fits into where the elements are. So what I'm essentially describing is the valence shell electron, or it's the very last set of electrons that you are putting in. So if you are looking at, for example, sodium, then you assume that everything you put in through neon, and then the last electron fits into the state that's corresponding to that. So when you label when you mark up the periodic table that way, this is how you would see it. The numbers here, these row numbers, they actually nicely correspond to, these are equal to the quantum number n. With, I think there's one little exception. You have to worry about when you come to here. We'll get to that. But except when you come to here, they correspond to quantum number n. And though the columns correspond to different orbital angular momentum states. So the first 2 columns correspond to orbital angular momentum L equals 0 state, with the exception of helium, which really ought to be here, but blame the chemists. So at least if we want that to work out right, the helium has to fit in here. Okay? So everything that's here, these 6 columns here, they correspond to where the last electron you put in has angular momentum of 1. Because starting with so with the angular momentum magnitude to 1, you have the projection values -1, 0, +1, and each of these have possibility of 2 possibilities for spin projection, so that's the 6. So when you come here, you have filled up this angular momentum state. Now, when you look at this, you will notice, so let's just start going down and see if this matches up with all the rules we know for these quantum numbers. These are the rules that you have been given the first time we covered it. So the principal quantum number, they start from 1 and 2, and it just goes up without really an upper limit. L, it goes from 0 and up to n minus 1. And the projection, it goes from 0 all the way to plus minus L on either side. So let's see if going through this periodic table, it looks like they are filling up according to these rules. So with n equals 1, we have only L equals 0 as possibility. And that's what you're filling up on the first row, if you move helium over here. with n equals 2, you have possibility of L equals 0 and L equals 1. So you fill the L equals 0 here, and then L equals 1 here. Now, with n equals 3 here, you have the same possibility as before, L equals 0 and L equals 1. Are we missing something? L equals 2, right? With n equals 3, we should have had L equals 2. It turns out, so L equals 2 is the what chemists call d orbital. It's the 2, so it has 5 different projection states. So with the spin, there's 10 different spots. It's this, I don't know what you call these columns, transition or whatever?
Transition metals.
Okay, sure. Transition metals, thank you. So just so that it's clear, these here, they don't have n equals 4. They actually have n equals 3 and L equals 2 quantum numbers. And when you write out the electron configuration, you see that. You write it down as a 3D something, right? Yeah. So I guess there's a bit of a jumping in front of the lines here. These, which have the quantum numbers n equals 4 and L equals 0. When you put in these, so let's say you filled up all the n equals 3 orbitals, and when you put in one additional electron, it turns out the lowest energy state you can get is not this one, which has lower value of n, but it's actually this one, which has higher value of n, but smaller value of orbital angular momentum. I don't quite remember why that is. I don't quite remember why that is. I just know that that's why. That's why these two orbitals fill up before you start filling up this other lower n value. And this kind of one offset, it continues throughout the rest of the sequence. So when you look down this here, they all have n value of 1 less than what you would have guessed. So, and when you go to n equals 5, I think the same thing happens because then, so this is n equals 4. So, at some point, a nice little rule that we had that worked really well for the first 3 rows start to break down because you have so many electrons. Now there are exceptions. It becomes a complicated calculation to figure out actual energy levels for the actual atom, multi-electron atom you're dealing with. So that's why in physics, we start with the hydrogen and we stop there. We don't want to deal with more than 1 electron because it gets too complicated. But at least for the first 3 rows, you see nice following of these rules without any exceptions. And starting with the row 4 is where you start to see some exceptions, but you can kind of explain it, chemists explain it, take chemistry if you're interested. As you get to heavier atoms, this is where you really take an entire course on it, because as you get to heavier atoms, you will find that the electrons have enough kinetic energy that you really have to start taking special relativity into account. So we are going to stay in this nice region. Any exam questions I ask you, it'll all be about hydrogen, not any other atom really. But you should know, so the most I expect you to know is sort of know what the quantum numbers stand for and how that corresponds to this periodic table of elements. Because this is the major accomplishment of quantum mechanics. What chemists took for an experimental fact, the quantum physicists were able to explain based on very elementary principles.